Our structure from motion algorithm is based on the insight that the observation matrix that we talked about has a very special form. In particular, it has a very low rank. So before we can look at the rank of the observation matrix, let's talk a little bit about the rank of a matrix. So first, let's talk about linear independence. A set of vectors v1 through vn is said to be linearly independent if no vector can be represented as a weighted combination or sum of the other vectors. That's basically linear independence. So let's take a look at some examples right here. So here are 5 vectors in a two-dimensional space. You have I, j, v1, v2, and v3. Now if you look at I and j, these are linearly independent because you cannot express I as simply a weighted scaled version of j because they're orthogonal to each other. If you look at I, j, and v1, indeed you can express any one of them as a linear combination of the other two, and so they are linearly dependent. If you look at I, j, and v3, the same. You can express any one of these as a linear combination of the other two, so it's linearly dependent. And if you look at v1, v2, and v3, the same applies. You can express any one of these 3 vectors as a linear combination of the other two, so they're linearly independent. So that should give you a sense for the difference between linearly independent set of vectors and linearly dependent set of vectors. So that now allows us to talk about the rank of a matrix. So let's say you have a matrix A, and it happens to be an m by n matrix. That means it has m rows and it has n columns. So you can write this matrix as a concatenation of these column vectors right here, and that would be n column vectors, or m row vectors right here, r1 through rn. And so you can say that the rank of a matrix, this matrix right here, you have 2 types of ranks. There's the column rank of the matrix, and there's the row rank of the matrix. The column rank of the matrix is the number of linearly independent columns of the vector of the matrix. And the row rank of the matrix is the number of linearly independent rows of the matrix. So those are just definitions right here. So now, the column rank of A must be less or equal to n because there are only n columns in A. The row rank of A must be less or equal to m because there are m rows in A. And it turns out, and this is important, that the column rank of A is equal to the row rank of A for any matrix, and that's the rank of A. And it is less or equal to the minimum of m and n. So this is the property of the rank of a matrix that we're going to use. So let's sort of visualize what this really means. Let's take the case of a 3 by 3 matrix here. Let's say A is a 3 by 3 matrix. And these are the columns, 3 column vectors, A, B, and C. So the rank is the dimensionality, if you will, of the space spanned by the column vectors or the row vectors of the matrix. That's the way to visualize it. What is the dimensionality? How many of these vectors do you need to span the entire space of vectors? So what does that really mean? Let's say that A, B, and C happen to be collinear, lined up this way. Then all you need is one vector to be able to express all the other vectors. You can simply scale it and you know what the other vectors are in this case. Therefore, all you need is one dimension to span the space of these 3 vectors. So the rank of A in this case is 1. Now in this case, let's assume that all the 3 vectors lie on a plane. It's a 2-dimensional plane. So any 2 of these vectors can be used to express any other vector that lies on this plane. So the space spanned by all these vectors has a dimensionality of 2. You need 2 of these vectors. So therefore the rank of A is 2. Now if you look at 3 arbitrary vectors in 3-dimensional space, then you need 3 vectors, all 3 vectors, to be able to express any arbitrary vector in this space, and therefore the dimensionality of this particular space requires 3 vectors, and therefore the rank is 3 in this case. So that is sort of the geometric meaning of the rank of a matrix. Now, the rank has certain properties, so let's look at some of these properties. The rank of A transpose is equal to the rank of A. We know this from what we just said. The column rank is the row rank, which is the rank of the matrix, so this comes straight from that. And then if you take the product of 2 matrices, and this is a property that we'll use shortly, if you say that you have a matrix that is a product of the matrix A, which is M by N, and B, which happens to be N by P, then the rank of that product is the minimum of the rank of the matrix A and the rank of the matrix B. And so therefore, we know that the rank of the matrix A has to be less or equal to the minimum of M and N. The rank of the matrix B has to be less or equal to the minimum of N and P. And therefore, the rank of this product must be less or equal to the minimum of M, N, and P. And now if you look at A transpose, from all of this, we can show that the rank of A transpose is equal to the rank of A transpose A, which is equal to the rank of A. And finally, if a matrix A is invertible, it's non-singular, it's invertible, then its rank is M. So such a matrix, of course, is a square matrix, M by M. If it's invertible, then its rank is equal to M. It's full rank matrix. Okay, so now let's come back to our observation matrix, W. We remember our observation matrix. You have U's and V's in the observation matrix, and these are centroid subtracted coordinates of feature points. And this chunk right here, the first top half of the matrix has the U's, the bottom half has the V's. So that's the matrix, observation matrix W, which is a 2F times N matrix. Remember, F is a number of frames, N is a number of points, scene points that we are trying to extract. And then we have our camera motion matrix M, which has all of these camera orientation vectors, unit vectors, I and J, all stacked up, so that's 2F times 3. And the most important matrix to us is, of course, the scene structure matrix S, which is 3 by N, 3 coordinates for each one of the scene points, and we have N such scene points. So that's our observation matrix. So now let's take a look at the rank of the observation matrix. We know W is a 2F by N matrix. We know that M is a 2F by 3 matrix, and we know that S is a 3 by N matrix. And using the properties we just discussed of the ranks of matrices, we can figure out what the rank of W is. So essentially, the rank of W, which is the rank of the product of these 2 matrices, must be less or equal to the rank of M and must be less or equal to the rank of S. We know the rank of M must be less or equal to the minimum of 3 and 2F. The rank of S must be less or equal to the minimum of 3 and N. And we're taking the product of these 2 matrices, and therefore the rank of the observation matrix W must be less or equal to the minimum of 3, N, and 2F. Now you know that we probably have a lot more than N points in the scene that we're interested in recovering, and we have captured in our video several frames, certainly more than 3. So what is interesting here is that the rank of the observation matrix W must be less or equal to 3. So we're going to exploit this to develop our factorization algorithm for structure for motion.